Welcome to the engineering deep dive on my Lego sorting machine. If you haven't already seen part 1, either click the link in the description or up here to go watch that first for an overview on the machine. But now let's dive into the different subsystems and the engineering behind them. Each of these C channels is driven by a stepper motor, and there is a gear reduction in the base. So you can see that the rotor that's rotating underneath there, it has teeth in it. And so within this assembly right here, the stepper motor has a gear, it drives a bigger gear, which drives this actual stator. The carousel is directly connected to the shaft of another stepper motor that allows for the trays to actually rotate around. You can see that each tray has a wheel connected to it that rolls on this cam. And that cam notches out there. So you can actually see that's what allows the trays to drop the pieces. Now for an overview of the electronics. So the main compute on this machine is this old NVIDIA AGX Xavier that I had lying around. It is running Ubuntu 20.04, and it hosts a web server on my local network that allows me to do everything that I need to do with the machine. So whenever the machine gets plugged in, this NVIDIA box will automatically start up and start hosting that web server so that I can access that with any device on my network to control the machine. Now connected to that are two USB-C hubs. One of them is right here. It's got a little Logitech dongle there so that I can actually use it with a monitor, keyboard, and mouse if I want to. And actually the USB hubs are daisy chained. This plug right here actually goes to another USB hub that connects to all of the low bandwidth sensors and components on the machine. Here is that other USB hub. You can see it's getting power. It's getting power right here from the Anchor power brick, and then all of the various USB cables. So specifically 3 of those cables are going to the cameras that are on the feeder, and 2 of those cables are going to the Raspberry Pi Picos. This other USB cable is a direct connection to the high-res camera that is in the classification chamber. And then this USB-C that's there, that's actually for power. Rotating the machine a little bit, I'm getting power from this Anchor power brick. So the USB-C is going to power that NVIDIA box, and then the USB-A cable is going to power the USB hub that I referenced earlier. I've just got a power strip connected to the machine here so that there's one power cable that goes to the outlet, and then that powers the Anchor brick, and then the other power goes to this Ender 3 power supply that supplies the machine with 24 volts, which is the main power rail. After that extension cable and the power supply, I do have this custom 3D printed case for a DC to DC power supply that will drop the voltage from 24 volts down to 6.5 volts for the servos. So after that DC to DC converter, we can go over here to where we can see the custom boards that John designed. So these are based around a Raspberry Pi Pico that you can see right there. That's about a $10 to $15 microcontroller. And with the blue heatsink on it, that is a TMC stepper motor driver. So we have slots for many of those. With the red light up there, that is a servo driver that can drive up to 16 servos. And all of those PWM signals get broken out on that gray ribbon cable. So that gray ribbon cable goes up, and that's actually all of the signals that go to the central chute. So all of the servos are actually on the central chute itself to control those flaps. And so that was one of the interesting mechanical aspects of the machine, is we need to get power and signals onto a rotating central chute. And so this was another one of my contributions. It's a newer one, but this green cable chain to actually protect the ribbon cable and allow for the cable to rotate around the chute as the chute moves. So you can see that cable, that cable chain protects the ribbon cable and allows for all of the freedom of movement needed by the actual central chute. Now up here you can see another one of the custom boards that John created. This allows for each layer. Each layer gets one of these boards, and it breaks out signal and power to the actual servo. You can see there's a servo motor right there that connects to a coupler that will control the flap that will divert pieces down this funnel here. Here's a closer look at one of those custom boards that is on each layer. So you have the ribbon cable going in, 2 ribbon cables actually, and then you connect the servo here. You can see that one trace that pulls out the one PWM signal, and then all the other PWM signals get jogged over one spot so that when it goes to the next tray, the next signal is always closest to where the servo connects. So back over here, I have another little custom 24 volt rail to break out 24 volts, all the different parts that need it. In the back there, you can actually see I kind of designed it. So a couple of those connections actually have built-in resistors because some of the LED boards, specifically the LED boards that are in the C channel here, do not have built-in resistors. So we got to limit that current a little bit so the LEDs don't burn themselves out. This is another duplication of that. The same board is on the left and right. They're just turned 90 degrees. The board on the right here is actually for the feeder, and the board on the left is for the distributor. So the distributor, it needs one stepper for actually turning the chute, and then it needs the PWM signals for the servos. And on the feeder, we actually have four stepper motors. So you can see on the left side there, all of those blue heat sinks are each individual stepper driver modules. The rear one is for the bulk C channel. The next one is for the second C channel. The third one is for the third C channel, and the fourth one is for the carousel motor. Recently, I've connected, you can see these brown wires here. These are actually connecting the diag pin for diagnosis of any faults. Specifically, so I have those all connected to the GPIO, free GPIO pins. And I'm working on getting stall guard enabled on all of these stepper motors. So that will allow the steppers to automatically detect whenever they're moving if they stall. So if a piece gets wedged, say when the chute is rotating, if a piece gets wedged in between the funnel and this bin, actually right here is like a good example. So this bin is almost full. So if another piece comes in here, there's a chance that would actually cause the funnel to kind of get clogged when it goes to rotate to the next position. And so the machine will now be able to detect that case and safely pause and notify the user to go address the clog. In the meantime, I just kind of go like this. Maybe once an hour I'll come check the machine, kind of do that just to clear that out so the machine can keep sorting. By far the most difficult part about building a Lego sorting machine is the singulation, where you take bulk Lego pieces that can be anywhere from the size of a baseball down to a little feather in a cap the size of a fingernail. And you have to separate those so that you reliably get one piece at a time being fed into your classification system. Once you classify it, how you distribute it into bins and sort it is entirely up to the user. The way that I sort it right now is based on category. So all pieces of the same shape and the same type will go into one bin. Say sloped pieces or plates or minifigure parts. Those each get sorted into their own categories. And then what I do from there, since my machine is around 93% accurate, I'll take those bins of say all the minifigure pieces, and then I can very easily manually pick out any of the pieces that are incorrectly sorted into that bin. And then from there, I can sort everything the rest of the way by hand. I can pick out all the torsos, I can pick out all the legs, whatever. But once you have a machine that can actually mechanically sort the Lego, like I said, once you have the piece identified, how you sort it is entirely up to you. So with only software changes, it could easily be implemented such that you can sort by piece price, you can sort by set. Say put all of the pieces for the X-Wing into this bin and put all of the pieces for the Millennium Falcon into that bin. Additionally, if you had a large set like the Millennium Falcon that comes with lots of numbered bags that are meant to be built in order, and you only open, you know, some subset of the pieces at one time when you're building, you could easily also program the machine to put all of the pieces for bag number 1 into one bin and all of the pieces for bag number 2 into a separate bin, and break it up like that, so that's much easier to reassemble larger sets as well. Let me tell you how I got involved with this project. So it all started 8 months ago, back over Thanksgiving break in 2025, when I saw a YouTube video posted by Spencer about his Lego sorting machine. He basically described and showed a Lego sorting machine that mostly kind of worked. It sorted about one piece every 30 seconds, but it had a lot of flaws and it would be very hard to reproduce. So he proposed that we as a community of engineers who want a Lego sorting machine come together and try to design a common open source Lego sorting machine that anybody could build with access to a 3D printer and a home improvement store. I've always played with the idea of building my own Lego sorting machine that could help me inventory my Lego, but I never thought that I would actually get to a point where I could build the entire machine end to end. And that's why I'm so thankful that I found this project with people that are all in the same boat. Engineers with very specific skill sets, be it in electronics, hardware, mechanical design, software design. Everybody is able to contribute their area of expertise and benefit from other people's areas of expertise. And the end result is that we all have a common Lego sorting machine that has the best of all of those different subsystems in one. This Lego sorting machine was designed by people around the world volunteering their engineering time to design a common open source Lego sorting machine that anyone can use. It's impossible to name everybody who's contributed, but I'm going to give a couple people a quick call out. So Tobias came up with the initial idea that kind of allowed us to hone in on these circular C-channel designs. Mark took that idea, ran with it, and was able to get the actual designs, the CAD, in place for these C-channels. The distribution was primarily designed by Nick, and Tom helped with that a lot too, I believe. Chris helped design the interface layer that connects the chute that moves and rotates to the rest of the machine stably. Spencer also was a major contributor in all aspects. He's the one who kind of kicked off this whole program and kept everybody aligned around meeting our goals. All the electronics on the machine would not have existed without all of John's amazing help creating those custom boards. Jose also helped with a lot of the low-level firmware. These C-channel camera mounts are one of the contributions that I made to the project. The C-channels all have these notches available around them to allow for mounting of different things like these legs or the little ramps here. What's nice about these C-channel camera mounts is that you can choose any two available positions, any two available of those little notches, and connect the mounts to that. And regardless of which two you choose, you'll still be able to join up the camera mounts in the middle to guarantee that the camera is located at the optimal position for watching the C-channels. I reused that camera mount to also keep an eye on the carousel tray to identify when a piece has fallen on the carousel tray. Another engineering contribution that I made was with these support wheels here. So these little arms here hold these wheel bearings that rotate on this raceway that's attached to the central chute. So that makes sure to support the weight of the central chute and also to kind of constrain its horizontal movement. And the previous design for these had these two plates. So this part here actually would attach to the frame, kind of in this orientation over there, you can see. And then it would take this plug in like that, and then the wheel would be mounted at the end. One issue with this was the way it got installed is it has to be installed this way, or you kind of, because that orange raceway kind of would get in the way, you would actually kind of force it in horizontally and get it in place like that. But that would actually cause the pieces to kind of wear out. And so what I saw is as my chute would actually rotate, this piece would move back and forth, and that wasn't giving the support that this thing really needed. So I designed the piece to actually be like this, where you could install it like this, where it's not getting in the way of that bearing race. So it's actually able to go in parallel. The screw that holds it is an M5, so it's a much bigger screw, much stronger. And you can see this support is much broader here. So there's no play there. And so that change has been, that has worked really well on the machine. Another contribution that I made to the mechanical design is on these brackets here. So I printed out an early version of these brackets, and it was actually kind of difficult to assemble these machines because all of the different degrees of freedom that these pieces had, because the inside of this bracket here was just a flat piece of plastic, and so it wanted to angle up and down relative to the extruded aluminum. And so I actually made the suggestion of adding tabs like this to all pieces that kind of interface with the extruded aluminum. And so now all of, like, I didn't do the redesign work, other people did that, but all of these brackets now have those little protrusions that lock into the channels in the extruded aluminum, and it makes putting the thing together a lot easier, and that adds extra stability and enforces the right geometry of the machine as you assemble it. One of the last contributions that I made on the mechanical side that comes to mind are these wheel adapter brackets at the bottom. And so one of the requirements for my machine is that I can transport it easily, especially in my car. And the existing wheel brackets were so tall that it actually made the machine too tall to fit into my vehicle without further disassembly. So I redesigned the piece, instead of being this long piece that would have the wheel then mounted below that, to this orange piece. However, the wheels are still easy to remove. So you can see right there, it's a standard office chair wheel with this little clip-in, and there's just a hole in there that allows for you to easily plug the wheel in and take it out. And then some of the wheels also are locking wheels. So once you get the machine into a position you want it, you can lock them in place, and it's good to go. Also, I modified my bins to have these little label holders so that I can label what each bin's contents are. It makes the machine a lot easier to use in the way I want to, which allows me to sort all pieces into one of 24 different categories by piece type. Another modification needed for my machine due to some certain clearance issues is actually this slice away out of the servo housing. So I was getting some interference between that and these arms. So basically slicing off that portion cleared out that issue. I also was having issues where the servo coupler was interfering with the wheel and the screw that were holding this ender wheel in place. So I made a smaller version of that coupling. And then here's another angle of the ribbon cable chain that I designed. So you can see it's working pretty well in there. But here is just a small portion of it. You can see up closer. So I designed it so it could actually be printed in place, already assembled. There were some supports needed in between each section here because there's kind of like that overhang. But once you knock those out, which takes a few minutes, you're able to kind of snap the chain to break it in, and then it works. You feed the ribbon cable through one end, and that keeps it pretty well shrouded, and it still allows for pretty tight angles of movement, which is really nice. So once the machine is powered on, this is the web page that I come to. Since my machine is already set up, typically I'll just go right to click Activate Sorter. However, I'll kind of show you guys through some of the setup and calibration that is in place. If the cameras get plugged in the wrong order, or whenever you take apart the machine and kind of put it back together, sometimes the camera indices will change. So this allows you to assign each camera to its location appropriately, so the machine knows which camera to use for which position. So that's pretty useful. The next thing is to actually draw some polygons onto some of the camera frames. That tells the machine where it should actually look within the camera frame for Lego pieces. There's a polygon for each of the 2 C channels that have cameras on it. There's a polygon for the carousel itself. And then there's a polygon for the classification chamber. Now, sometimes these need to be tuned. Like you can see, it's a little out of alignment right now. However, I can go to the machine and I can kind of make sure that the carousel is aligned correctly before I start it. I do plan to make that automatic in the future using stall guard. You basically draw the box where you want the camera to focus and it'll pay attention in those areas. Additionally, on the 2nd and 3rd C channels, you get to specify the receiving zone and the feeding zone. So the receiving zone is where the C channel receives pieces from the previous C channel. The feeding zone is the region where the camera is going to tell the C channel to move slowly because pieces are within the feeding zone. And the goal of these channels is to feed one piece at a time. So to ensure that only one piece gets dropped, it's important that the C channel slows down when there's pieces in the feeding zone. The receiving zone is used to tell the previous C channel when to deliver more pieces. So if this C channel already has pieces in the receiving zone, then it's going to tell the previous C channel to not feed any more pieces because it's got to take time to actually spread those out and deal with those. Now, the last script is a script that I have tuned a lot. This will gather the baseline for the carousel camera and or the classification camera. Since my version of the machine still kind of depends somewhat on ambient lighting, specifically the carousel camera, you could see that on the previous one here. So the carousel camera, like it's mostly illuminated. There are some lights built into the machine, so it can still operate in the dark, but ambient lighting also adds or takes away from this image. So if ambient lighting in the room changes significantly, going and recalibrating this image might be necessary. So once you decide which camera you want to do the calibration on, you can actually go and capture the baseline. And so what that's going to do is it's actually going to move the machine. So I'll go ahead and start it and we can take a look. So it will actually cause the carousel to rotate. And every rotation, an image will be captured in the classification chamber and the carousel camera. And those images are all kind of being added up to kind of define what a generic, what the generic empty background looks like. And now you might see that the machine is also kind of wiggling. And that's because I'm intentionally causing the chute to oscillate back and forth. And those oscillations can actually be tuned in here to kind of find whatever works the best. But right now I have it oscillating at 50 hertz and the amplitude is 60 microsteps. And that actually induces like some vibration in the machine, which happens during normal operation as well. So a classification wouldn't be as accurate if the machine is totally still, because during operation, that's not what it looks like. So it's important that I found that it actually helps a lot to induce some vibrations into the machine during the classification baseline, because that will actually cause the trays to be in like slightly different positions, which will help a lot more with the mapping of what a empty tray looks like. And then at any point you can always stop it early, and that will trigger the round to be saved with whatever data is there. So you don't have to wait for the full 64 to complete. What was there was saved and will be used as the baseline. So now that the calibration baseline is complete, we should be good to activate the sorter. However, there are other tools that can be useful in either debugging the machine or getting the machine set up. Most of these I don't need to use regularly anymore. However, if the machine gets taken apart and put back together, sometimes some of these tools are useful. So if there's ever issues with detecting pieces, using this tune detection actually shows a lot of the different inner workings of the detection algorithms that are running on both the classification chamber and on the carousel tray. Right now you can see there are no detections, but if I place an object onto the tray, you can see that detections are now showing up. So you can see those objects are now getting detected there. We can look in the classification chamber too. We can see those. So yeah, that is a very useful tool available. Another tool that's available is this camera control. So you can see it right now, it like defaults to some crazy values here. But this allows you to change all the different settings available on these cameras. And so that helps to actually tune what is the best setup for these cameras. My goal, so I've done it manually, like I've manually gone through and like set these values, but since the machine can actually run automatically, I actually want to automate the camera tuning to happen over time, where, you know, I'll tune it to manual values to where it looks pretty good. And then the machine will spend 20 minutes, you know, with a slightly different exposure. And then it'll spend 20 minutes with a slightly different white balance. And it'll actually test out different values to see if during those tests that the accuracy of the machine went up at all. And it can actually be like fully automated tuning of the machine. So that is one place that I want to get to. Another thing is this auto color calibration. So because we want the machine to be able to detect colors appropriately, there's actually a color calibration target that I've created that has white, black, light gray, dark gray, red, blue, green, and yellow tiles on it. And so I can actually set that up in the frame, and then it'll have you click the 8 different colors, and it'll then go through and automatically change some of those same variables that were available in that other camera calibration script. The hue, the saturation, exposure, white balance, all of those different things, and it will automatically try to find the best values that are able to still distinguish all the different colors. So this is a pretty useful script for color detection. Servo diagnostics is essential because the servos are rigidly attached to the chute flaps that divert the pieces. If you tell the servo to move outside of the range of the flap will actually shear off. And the servos do not have any type of feedback to the machine to tell it when, you know, what torque it is putting out, or if it's detecting any resistance. And so it's very important that the servos only be commanded to move within the allowable range of motion. And so this script actually will wiggle the servos, so it'll toggle between the open and closed position, and you can actually change that. So whenever I take apart the machine and put it together, I will have both servos move near the very center of the range of motion. That should always be a safe location for the servo to move within the flap's range of motion. And so I can do this, and I'll click wiggle, and that will actually make the flap open and close and open and close, and I can see where it is. And while it's wiggling, I can slowly change these values to get bigger and bigger to make sure that the chute actually wiggles only within the range of motion and not too far. And once I'm happy with that, I can go ahead and click save. And then I can go to the next one and the next one, etc. Another tool available is this chute calibration tool. And it will actually do some checking of the wiring to make sure that like things are moving as expected. It will only allow certain movements before the limit switch is actually verified with hardware. And so you can jog the chute manually, and if you jog it until the switch gets clicked. So once the switch gets clicked and held for a second, that then says that the switch is verified, and you can always see a live readout of the limit switch status here. So I can back it off to where the switch is open, or I can jog back to where the switch is closed. You can also run a sweep if you want. You can tell, once the limit switch is verified, you can tell the machine to home the chute, and so it'll actually quickly move to where the limit switch is. It'll engage the limit switch, and then it'll back off, and then very slowly engage the limit switch to get a good, accurate homing. And I also configured it so you can tell it to home either in the clockwise or the counterclockwise direction. And then you click this home button, and it will actually do that homing movement. Once the chute is homed, and again, this is kind of like machine setup stuff. You don't have to do this every time. It's just kind of like a first time thing. Once the switch is homed, you can jog the chute in different directions, and you can get it so that the funnel is directly aligned with one of the bins. And you can actually choose how many bins you have in a given section. And so my machine right now has 2 bins per section, so I select that. And then once you get it aligned with one of the sections, you can choose which section you want it to be. So the sections are the edges of the hexagon. The hexagon has 6 sides, so there's 6 sections. And then within each section, you have multiple bins. I have 2 bins per section. And so you can choose which bin it's going to. And then you can also choose whether you want the bins to get indexed in the counterclockwise or the clockwise direction around the machine, because different people might have different preferences. When I look at the bins in the machine, I like them to increment going towards the right. And so that actually has them increment in the counterclockwise direction. But once you get that aligned, you can click compute mapping, and it will actually compute all of the angles of all of the bins for the machine, which is really nice. And if you want, you can adjust the angle offsets between the bins. In a machine that has 2 bins per section, through trial and error, I was able to see that a 27.3 degree angle between bin A and bin B is the correct angle between those sections. But if you have a higher number of bins in your section, if you have 4 or even, let's say, 5 bins, the angle between those bins is going to be much smaller. And so you can actually fine tune that. It'll automatically calculate that. Even if you just get it aligned to, say, bin D, you can say, okay, right now the chute is aligned to bin D. Go ahead and calculate that, and it'll calculate all the angles for you automatically. And save those so that when you go to actually use the machine to sort, it'll know where to align the chute for the bins. I also have this toggle switch here for saving training images. So as I sort my pieces, every image that gets classified, I also save a copy of it locally, just so I can always go back and, fine tune that in the future if I want. There's also a tool here for building the firmware for the Raspberry Pi Picos. So since I have 2 boards, I have a feeder board and distribution board. I can build for either of those, and then I can flash them. It is important that only one Pico be connected at a time during the flashing, but it'll check for that. And then the last tool that I'm still in the process of debugging and getting working is this stall guard tool. I'm trying to get this enabled, but the idea is I got the wires connected for stall guard, and I want to basically set the running current. So while the stepper moves, you can control, based on the stepper control modules, you can actually set how much current to send to those steppers, which directly translates to torque. And my thought is, if you set the current to be very low, so basically you're sending very little torque to the motors, that'll make it a lot easier for them to stall. My goal is to get it so that the machine can automatically calibrate and test that stall guard is working without me having to go touch anything or clamp down a motor to make it stall or anything. And that will allow the machine to be much more easy to operate when I'm not right next to it. Because right now, if a stall happens, my only notice is the sound that the steppers make when they start skipping steps. And so that indicates to me that I have to pause the machine and then go check to see what stalled. Usually it is because one of the bins filled up so much because I sorted so many pieces that one of the pieces is now actually backing up into the funnel. And so when the distribution system drops the piece in, the piece doesn't fully go into the bin. And when the funnel that's attached to the chute goes to move to the next position, as the chute rotates, that actually wedges the piece between the funnel and the bin, and that causes the chute stepper motor to stall. But now we can go ahead and activate the sorter. So as we do this, the C channels are going to back up about 10 steps, and that will ensure that any pieces that were like clumped up or about to drop kind of get cleared back in the C channels to give them time to actually like properly queue up before dropping. And also the chute will go and home itself, so it knows exactly where it is at the beginning. But then we can come to the standard web page where I'll actually leave everything running. So like when I run the machine, this web page I just always kind of keep opened in a tab. And I can click this play button at the top right, and it will go through and it'll start running the machine. So I have added some stats to the machine. At the top, you can see that I've sorted almost 3,200 or almost 32,000 pieces. The unknown pieces are what happen when a piece is detected on the tray, but when we send that picture out for classification, Brickignise is not able to have a high enough confidence level in what that piece is. So that is an unknown piece. A rejected piece is when Brickignise is able to classify the piece, but the piece does not fit into any of the category bins that I have allocated. And so far all of my pieces have been, have fallen into categories that I've assigned. The not found pieces are what happens if either the detection model cannot see the piece on the tray, or what usually will happen is the tray is actually empty. So in the past, I had some issues where a piece overhanging in C channel 3 would actually cause a detection to be found on the carousel tray, even though the piece was still on C channel 3. And so the carousel would think a piece was present and send the tray, but the tray would still be empty. And so there was a couple of times where I didn't notice that was happening for, maybe 10 minutes, and it just kept sending empty tray, empty tray, empty tray. So that's where all those not founds came from. I also have a running stat of pieces per minute. This is calculated over the most recent 200 pieces sorted. It averages. Same with all of these carousel wait times, so I can get a better understanding of where time is being spent in the machine. Now I will say that this piece per minute is a little low for what is average on my machine these days. I'd say 8 pieces per minute is pretty close. I've even seen it as high as like 9.3 pieces per minute, which is well over 500 pieces an hour, which would be awesome if I can maintain that. So as I'm further trying to tune my machine, that's where I'm looking at these different times here. We can see a lot of the time right now, the carousel is waiting for the C channel to actually give it a new piece. So I'm working on trying to figure out how I can optimize those pieces being delivered to the carousel. And as I'm tuning, trying to deliver more pieces to the carousel, I am doing that. However, now you might have noticed that there's a decent number of double feeds, which also is not helping the problem, because the whole point of the feeder is to deliver one piece at a time. And if the feeder is not doing that, then you're not able to sort one piece at a time, which kind of defeats the purpose. So like right here, you can see it delivered 2 pieces, and what typically happens, one of those pieces will be identified, and then both pieces will go to that bin. And so that would be one accurate sort and one inaccurate sort from my metrics. So another thing that I want to add detection for is dual feeds. I don't believe that'll be too difficult. You can see here in the heat maps, there's pretty distinct objects here. So I think if I can I'll basically have the program say, whenever there are two non-connected objects detected, to try and classify each of those individually and then decide what to do with them at that point. And that's the end of our engineering deep dive. If you'd like to follow the project, find a link to the Discord server in the description. Thank you so much for watching.